All right, so this is the part 2 of the question. Okay, so let's talk about the Vesper model here, because the Lewis structure and the Vesper model both are very important to determine the shape. Okay, so let's talk about the part 2, that is Vesper model. Okay, so the valence shell electron pair repulsion, that's what we call it as Vesper model. Okay, so this model focuses on the bonding and non-bonding electron pairs present in the outermost valence shell of an atom that connects with two or more other atoms. Okay, so fundamentally the Vesper model theorizes that these regions of negative electric charge will repel each other, causing them to stay as far as possible. All right, so there is a repulsion between the pairs of valence electrons in all atoms. Okay, so what are these valence electrons? We have two types of electron pairs. Okay, valence electrons, and we have two types of these valence electrons pairs. Okay, the first type is the bonding electrons, which participate in this bonding of two atoms or three atoms. Okay, and we have lone pair atoms. Okay, so lone pair electrons. Okay, that is called the second type of electron pair is called lone pair. Okay, lone pair electrons. Okay, so these lone pairs, they wouldn't participate in a bonding, in a bond. Okay, so they wouldn't participate in a bond. Okay, so those are called as lone pair. Okay, lone pair electrons. So these are the two types of that valence electrons. Okay, so and the atom will always tend to arrange themselves in a manner in which this electron pair repulsion is minimized. You have to note this point. Okay, the atom will always tend to arrange themselves in a manner in which this electron pair repulsion is minimalized. Okay, this arrangement of the atom determines the geometry of resulting molecule. Okay, so now you can understand that there is some kind of a repulsion between electrons pairs. Okay, so we have lone pair electrons and we have bonding electrons. So we have two types of electrons. Okay, so if we take the lone pair electrons, the repulsion force, okay, the repulsion force between two lone pair electrons is very, very, very high compared to the bonding electrons, compared to the repulsion force between two bonding electrons. Okay, so if you put this, so the bonding electrons, I mean the repulsion force between two bonding electrons is actually the repulsion force between two bonding electrons is minimal, is small compared to the electrons repulsion force between two lone pair electrons. Okay, repulsion force between two lone pair of electrons. Okay, and the second highest is the repulsion force between one pair of bonding electrons and one pair of lone pair electrons. Okay, and the least force, okay, least repulsion force could be assigned to two pairs of bonding electrons. So that is the order. The reason why these lone pair electrons, okay, have these two or three or four lone pair electrons have huge amount of repulsion force is because these lone pair electrons are controlled by one nucleus. Okay, they are controlled by one nucleus because they are connected to one atom. Okay, so they are connected to that central atom, that one atom. Okay, so that central atom's nucleus only affect these electrons. Okay, so electrons automatically, this pair of electrons has a amount of substantial amount of repulsion force between them. Okay, and this nucleus is controlling them, but lone pair electrons has one control authority. They have this only one, this nucleus only. Okay, only this nucleus. Okay, so they are a bit powerful. They are a bit powerful compared to the bonding electrons, because the bonding electrons pair have two controlling authority, the nuclei of the two atoms which are bonding together. Okay, so those two nuclei will control these bonding electrons, so they don't have that much of power. So because of this reason only, the lone pair electrons has more repulsion force because they have less controlling authority. Okay, and the bonding electrons have lesser amount of repulsion force because they have two, or maybe they have more controlling authority compared to these lone pair electrons. Now you can understand why this lone pair of electrons are superior in terms of repulsion force. So here is something which you should remember, that whether it's say single bond or double bond or a triple bond. Okay, so all these bonds, okay, even the single bond and the multiple bonds. So multiple bonds are this double bond and the triple bonds. Okay, so all bonds are treated as a one repulsion unit, okay, or one Vesper unit. Okay, but the lone pairs are treated differently. Like if you have one lone pair, then you have one repulsion unit. If you have two lone pairs, then you have two repulsion unit. If you have three, then you have three repulsion unit. Okay, something like that. Okay, but for the bonding electrons, especially for the bonds, okay, you have one single bond or you have a multiple bond. Let's say you have single or triple bond. Okay, so those would be treated as one repulsion unit. Okay, so I'm talking about the bond or the multiple bonds between two atoms. I'm not talking about the bond between several atoms. Let's say we have CCl4. So carbon is the central atom and we have 4 chlorine molecules around it. Okay, so each has 4 bonds, 4 single bonds. Okay, that is different. So I'm talking about, okay, single bond or the triple bond or the double bond between two atoms. Okay, so whether it's single or multiple bonds, it should be treated as a one repulsion unit. Okay, simple. And I told you the example, that is CCl4. Okay, in that example we have 4 different single bonds. Okay, because each bonds connected to a different individual chlorine molecule or chlorine atom. Okay, so in that case we have 4 bonds. Okay, so in that case the repulsion units would be 4 repulsion units. Okay, so we have 4 different types of bonds there. Okay, under this Vesper theory, we have three things to note down. Okay, or three things. Okay, the first one is the electrons pair geometry. Electrons pair geometry. Okay, so this geometry is about the distribution of repulsive units. Okay, we spoke about this repulsion unit. Okay, repulsion unit is the one which repulse, okay, that is electrons. So we have two types of repulsion units. The first one is the bonding electrons and the second one is the lone pairs. Okay, so we have two types of repulsive units. Okay, so the distribution of repulsive units, okay, in the space around the central atom is called electron pair geometry. Okay, so this is what we call as electron pair geometry. The second thing we have here is the molecular geometry, okay, also known as the molecular structure. Okay, so this is a three-dimensional structure or arrangement of atoms in a molecule. Okay, so understanding the molecular structure of a compound can help determine the polarity, reactivity, phase of the matter, color, magnetism as well. So when stating the geometry of a particular molecule, it is necessary to report bonding angles. Okay, so when we try to establish the molecular geometry, we need to state the bonding angle as well. So that is the third one. Okay, so we'll talk about this later. We'll talk about this electron pair geometry and the molecular geometry later, and we'll move to the third part, that is the shape. Okay, so when we are asked about the shape, we just give them the shape only, the shape, the name of the shape. Okay, we don't give them the bonding angle. Okay, so these are the three things. Okay, the first one is the electron pair geometry and the second one is the molecular geometry, the third one, the last one, is the shape. So the final verdict is geometry of a molecule carries the shape and the angle. Okay, so geometry of molecule associated with the bond angles in Lewis structure representing the shape. Okay, shape of the molecule represents the Lewis structure in order to illustrate the shape without the bonds angles. Okay, and the third one, the electron pair geometry represents geometry of repulsive units. Repulsive units, I told you earlier, the repulsive units are, we have two types of repulsive units. The first one is the lone pair electrons, and the second one is the bonding electrons. These are the repulsive units. So the electron pair geometry represents the geometry of these repulsive units. So that is the short summary. Okay, so let's move to some example and let's figure out what exactly this electron pair geometry and the molecular geometry as well as the shape. Alright, now we have some steps to be carried out, okay, in order to find the shapes. Okay, so the first one is we have to draw the Lewis structure. So this is where this Lewis structure comes in. Okay, so I have explained you already. You can go and check the question number 5, 2010 chemistry past paper. You have to check the part 1 of the question number 5. In that I have explained the Lewis structure in detail. So with that, you have to draw the Lewis structure first. Okay, so once you are done with the Lewis structure, you have to count the number of electron groups and identify them as, say, bond pairs of electron groups or the lone pairs of electrons group. Okay, so that is the second step. You have to identify the repulsive units, how many repulsive units are there. So that is the second step. Okay, for that you have to identify the both electron pairs and the bonding electrons. Okay, The third one is name the electron group geometry. So we have, we have names like, linear, trigonal, planar, tetrahedral, trigonal, bipyramidal. We have octahedral. So these are the names of these, electrons. Name of some, electrons geometry, electrons pair geometry. Okay. Okay. So the last part is we have to see how many lone pairs there are. Okay, so we have to count that. So with that we can establish the molecular geometry. So I have a chart for that. So applying, your numbers to that chart, you could be able to find the exact shape of that, electrons pair geometry as well as the molecular geometry. This is very easy. Okay. Alright, so let's go with this example which was given in that question. Okay, the question was about SO32 minus. They were asking the shape of this SO32 minus. Okay, so let's make this as an example and let's learn this molecular and the electron geometry with this, and finally we can come up with the shape. So we have already established the first step. Okay, that is to establish the Lewis structure. We already did that. So we have already done the step 1. Okay, so we have established the Lewis structure. Okay, so this is the Lewis structure. So if you want to learn about this, you have to go and check the question number 5, chemistry 2010. Okay, year 2010. You have to check the part 1. Okay, so yeah. So now what we're going to do is we're going to do the step 2. Okay, so what is the step 2? What is the step 2? Step 2 is to identify the repulsive units, the repulsion unit or the repulsive unit. Okay, here we have to identify the repulsive unit for the central atoms. Okay, central atom. Okay, so here we have sulfur is the central atom. So sulfur has how many bonds here? Okay, sulfur has 1, 2, 3 bonds here. We don't care about whether it's a double bond, a single bond or triple bond. Okay, so as long as we have one bond, okay, one bond, whether it is a single, double or triple, we count it as one repulsive unit. Okay, as long as it stays between two atoms. So we have one repulsive unit here, and we have the second one here, second repulsive unit here, and the third repulsive unit is here, and we have a lone pair of electrons. Okay, that is also counted as a repulsive unit. Okay, so we have how many repulsive unit here? We have 4 repulsive unit here. Okay, let's say if we have another repulsive unit, another lone pair unit here, then we would count it as the 5th repulsive unit, but we don't have here because in this scenario we don't have any additional repulsive unit other than this lone pair. So we have only 4 repulsive unit. So let's refer the chart. Okay, we have a chart. Okay, that chart indicates all these electron pair geometry as well as this molecular pair geometry. So let's refer it, and based on that we can do this question. So this is that chart here. So this is that chart here. So number of electrons dense area means this is the number of repulsive units. Okay, so if we have 2 repulsive units, then the electron pair geometry would be linear. Okay, and here they have particularly separately mentioned lone pairs, number of lone pairs. Okay, so if we have repulsive units, if we know the repulsive units, the number of repulsive units, with that we can identify the electron pair geometry. If we know the types of the repulsive units, I told you, right, the types are the bonding electrons and the lone pairs. Okay, if we know the types of those repulsive units, then we can determine the molecular geometry. Okay, so in our case in SO3 we have 3 bonding pair electrons and 1 lone pair electrons. Okay, so for here this is the total repulsive unit. Okay, so we have totally 4 repulsive units in SO3 2 minus. Okay, so here this is for 4. Okay, so we have number of electrons dense area, in other words, okay, number of repulsive units. Okay, so we have 4 repulsive units. So the electronic pair geometry is actually tetrahedral, that is tetrahedral. Okay, but the question was not about the electron pair geometry, it is about the shape of that SO3 2 minus. So here we identified the electrons pair geometry, that is tetrahedral, and we know precisely the types of the repulsive units. Okay, so for SO3 we have 3 bonds. Okay, 3 bonding electron pairs, and we have 1 lone electron pairs. Okay, to identify the molecular geometry, all we need to know is the lone pairs. How many lone pairs there? Okay, so in our case we have only 1 lone pair, so that means here we have 4 repulsive unit, and one of them is a lone pair. So that means here you see, so I'll mark this. So here we have 4 repulsive units and we have 1 lone pair. So in our case we have 1 lone pair, so that means here, so the molecular shape is trigonal bipyramidal. Okay, that is the shape. Okay, so we can easily identify this. So we have found the molecular shape. So the molecular shape, okay, so I already told you that the molecular shape contains the shape of the Lewis structure and the bonding angle. So that combination is called molecular geometry. Okay, so actually it includes the shape and the bonding angles. Okay, so we know the shape here. So this is the shape. The trigonal bipyramidal is the shape. Okay, now in the question they are mentioning, they have given these 5 compounds. Okay, so we have to identify the shape of these molecules separately. So with that we can connect which one is similar to this one. Okay, let's identify the shapes separately for each compounds. Okay, so ClO3 minus. Okay, so here what we're going to do is we're going to establish the central atom. So here chlorine is the central atom. Okay, because that is the least electronegative one. So chlorine, and we have oxygen, and we have 3 oxygen. I'll put this way. Alright, now we have minus in this compound, so we have to mark that. So now we're gonna count the totals total valence electrons in this compound. The total valence electrons for the chlorine is 7. So we have 1 chlorine atom, so 7 into 1, that is 7. For oxygen, that is 6. We have 3 oxygen, 18, and we have one minus. If we have minus charge, then we add, you know, 1 electrons. Okay, so for minus, that is 1. Totally we have 26 electrons. Okay, so first we, you know, we distribute those electrons to the bonds. Okay, so I'll mark with red. So here 1 electron, 1 electron, 1 electron, 1 electron, 1 electron, 1 electron. So I make, you know, 3 bonds. Okay, I connected all these, you know, all these 3 oxygen to this chlorine. So I have spent, you know, 6 electrons. 1 2 3 4 5 6. So 6 electrons. So now I'm left with 20 electrons. Now I'm going to distribute these 20 electrons, okay, to these, you know, the most electronegative atoms. So here in this case we have oxygen. So I'm going to distribute those 20 electrons. Not actually, I'm going to first distribute some electrons to these, you know, electronegative atoms, okay, in order to fulfill the octet. Okay, until I fulfill the octet, I distribute these electrons. Okay, so once I'm done with the octet, I will distribute the remaining electrons to the chlorine. Okay, so that's how it is. So yeah, first, so for this oxygen, it has 2 electrons already, so I have to, you know, distribute 6 electrons to fulfill the octet. Okay, so 1 2 3 4 5 6. 1 2 3 4 5 6. 1 2 3 4 5 6. Okay, so totally I have, you know, used 18 electrons. So I'm left with 2 electrons. So these 2 electrons would be distributed to chlorine. So chlorine has, you know, 1 lone pair. So here let's go to that, you know, molecular geometry. That's mean the shape. Okay, so here we have, you know, we have 1 repulsive unit, this is the second repulsive unit, this is the third repulsive unit, and this is the fourth repulsive unit. So all together we have 4 repulsive unit. Okay, 1 lone pair. Okay, so let's go and check the chart. So we have 4 total repulsive units, and we have 1 lone pair. So that's mean we have the same trigonal bipyramidal. Okay, it's similar to that SO32 minus. ClO3 minus is similar to SO32 minus ion. Okay, the shapes are, you know, similar. The question is about, you know, whose shape is distinctly different from, you know, that of SO32 minus. So we have to identify the distinct one, the different one. Okay, so this is, you know, similar. Let's check for PCl3. Right, PCl3. Okay, so for PCl3, so P is the central atom, chlorine, 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 and P has 5 valence electron, 5 into 1, that is 5, and chlorine has, you know, 7 valence electron. We have 3 chlorines. Okay, 7 into 3 21, we have 26 electrons. Gonna distribute that to, you know, bonds electrons. So 1 2 3 4 5 6. So I have used 1 2 3 4 5 6 electrons. Now I'm left with 20 electrons. So here I'm gonna, you know, use remaining 6 electrons. 1 2 3 4 5 6. 1 2 3 4 5 6. 1 2 3 4 5 6. I'm left with two electrons, so I'm going to distribute it to phosphorus as a lone pair. So phosphorus has four repulsive units. Okay, one is the lone pair. It is same like this, four repulsive unit and one lone pair. So this is for one lone pair, trigonal bipyramidal, same as SO3 2 minus. This is same, this is also same. Now let's do it for SOCl2 minus. SOCl2. SOCl2. Here the least electronegative atom is the sulfur, S chlorine, oxygen. Sulfur is 6 into 1, 6. We have 2 chlorines, 7 into 2, 14. We have 1 oxygen, that is also 6 into 1, 6. We have 26 electrons, total valence electrons. So I'm going to make bonding electrons 1 2 3 4 5 6 electrons used. So now I'm left with 20 electrons. So I'm going to distribute to the most electronegative atom, so that is oxygen here, 1 2 3 4 5 6. Then to chlorine, 1 2 3 4 5 6, 1 2 3 4 5 6. Right. So I'm left with 2 electrons. So I'm going to distribute it to sulfur. So sulfur has this lone pair. So we have 4 repulsive units. One of them is the lone pair. It is similar to that SO3 2 minus. We don't need to check the chart. Now H3O plus. H3O plus. H3O plus. So oxygen is the central atom. Since oxygen is actually the most electronegative atom, so we can't make it as a central atom. But in this case we have to, because we have only one oxygen, and these are hydrogen, and hydrogen cannot bond more than one atom. Okay, more than one bond. Okay, it can make only one bond. So in order to make this compound, we have to make this oxygen as the central atom. Okay, so this is an exceptional case like water. So oxygen here, hydrogen, hydrogen, hydrogen. So we have to count the total valence electrons. So oxygen has 6 into 1, that is 6. Hydrogen has 1. We have 3 hydrogen, so 1 into 3, and here you can see the plus. If we have plus charge, then we have to deduct 1 electron. So we're going to deduct 1 electrons. So we are now with 8 electrons. So we have 8 electrons. So I'm going to make the bonds first. 1 2 3 4 5 6. Okay, so I have spent 6 electrons. Now I'm left with 2 electrons. So I'm going to put it to oxygen. Now we have 4 repulsive unit. Okay, 1 2 3 4. Okay, and this one is a lone pair. So we have 4 repulsive unit and 1 lone pair. That means it is similar to that of SO3 2 minus. So The solid answer is this one, NO3 minus. That is the answer. NO3 minus, sorry, not 2 minus, NO3 minus. Right, for nitrogen is the central atom because it's the least electronegative one. So nitrogen has 5 valence electron, 5 into 1, that is 5. Oxygen has 6, so we have 3 oxygens, so 6 into 3, 18. Now we have 24 electrons, okay, 5, 18, we have 23 electrons, and we have minus, right? So we have to add 1, so 24 electrons. Now let's make bonding electrons. Let's make the bond. 1 2 3 4 5 6. 1 2 3 4 5 6. 1 2 3 4 5 6. 1 2 3 4 5 6. So we have used 8 8 8, okay, that is 24. So now we are done with all these 24 electrons, right? So we have three repulsive units, okay. We don't have any lone pairs, we have 3 repulsive units. Let's check for the chart. We have 3 repulsive units, so the electron pair geometry is trigonal planar, and we don't have any lone pairs, so no lone pairs. So same trigonal planar, we have trigonal planar, okay. So NO3, the shape of the NO3 is different from the shape of SO3 2 minus. The shape of the SO3 2 minus is trigonal bipyramidal, okay. So this is also trigonal bipyramidal, this is also trigonal bipyramidal, this is also the same, this is also the same, okay. The different one is this one. This is this is actually the trigonal planar. This is actually trigonal planar. So the answer is the 5th one. So this is the answer.